Good morning. So what we are going to see talk now today, Adina, we are going to see our ADC and DAC in detail. So when you are saying about an ADC block diagram, that is we'll have often three process, one to be the sampling, another one to be the quantization, and other one to be the coder. So the first thing we all know that the thing is to be that we'll have a sampling. So which is so we have to give up an input signal to be the analog signal. Analog signal which is be giving to the sampling, so that is XA of t. So sampling is the conversion of continuous time signal into a discrete time signal obtained by taking the samples of continuous time signal at discrete instance. Okay. So then, so if the x of t is the input to the sample, the output is this x of nts, where t is called the sampling interval x. So then again, it has to be given to one quantization. So quantization, we know that that is the time period will be converted into one, this analog signal will be converted into one discrete time signal. So we'll be having of an x of n. So when you are saying over here, so the process of converting a discrete and continuous time amplitude signal into digital signal is called an quantization. So the value of each signal sample is represented by a value which is selected from a finite set of possible values. The difference between the unquantized sample and the quantized is called the quantization error or quantization noise, so which is nothing but an EQ of n is equivalent to XQ of n minus x of n. To eliminate the excess bits, either discarded them by the process of truncation or discard them by rounding the resulting number by the process of rounding. So thus the values allowed in the digital signals are called the quantization levels. The distance, which is delta between two successive quantization level, is called the quantization step size or resolution. So the quality of the output of the A to D converter is measured by the signal to quantization noise ratio. Whereas when you are defining the coding process, each discrete values Q of n is represented by a B-bit binary sequence. So we have a block diagram over on it. So analog preamplifier, sample to banding, A to D converter. So then we'll have a buffer. Then finally we'll have a computer or communication channel. So this is the process what which has takes place in order to conversion of an analog signal into an digital signal. So whereas in the case of an digital to analog, we'll have a digital input signal. Then again we'll be using of an D to A converter. Then we'll have a sample and hold circuit, and then finally we'll have a low pass filter. At last we'll have an analog output signal. Okay. So what will happen? The DTA converter will accept at its input electrical signals that corresponds to a binary word and which produces an output voltage or current that is proportional to the value of the binary word. Okay. So the task of D2A converter is to interpolate between the samples. So the sampling theorem specifies the optimum interpolation for a band limited signal. So the simplest D2A converter is the zero order hold, which holds constant value of sample until the next one is received. So additional improvement can be obtained by using linear interpolation to connect successive samples with straight line segments. Better interpolations can be achieved by using more sophisticated higher order interpolation techniques. Whereas in the case of suboptimum interpolation techniques, which results in passing frequencies above the folding frequencies. So such frequency components are to be undesirable and they are removed by passing the output of the interpolator through a proper analog filter, which is called as a post filter or to be named as a smoothing filter. So thus D2A conversion usually involves a suboptimum interpolator followed by a post filter. So this is the way which takes place in order to conversion of an analog to digital and digital to analog signal. Okay. The next one to be the digital signal processing system. So we know that what it will take place. So we'll have analog signal, just to be a continuous signal. So before, in order to give a fan sample and full circuit, we have to give it over to the anti-aliasing filter, and then after we have to give pass it over to the sample and full circuit, and then it is given to an A to D circuit. Finally, it is given to the DSP, and then we will be giving off an D to A converter, so that we'll have a reconstruction filter in order to get back our analog signal output over on it. Okay. And then what about the perspective of digital signal processing problems? So when you are saying about over on it, so we'll have in different applications areas. So we'll have often medical, and then radar, and then speech processing, seismic processing, and image processing. So these are all we'll having over on it. Whereas in the case of an basic functions, so we'll have an algorithm, we'll have a processor, instruction sets or hardware sets, implementations, architectures, component technologies. So these are all the ways in which we'll have a DSP characteristics. So whereas in the case of an DSP applications, application requirement process attributes, it is will have a real-time processing throughput, so which will have a high speed and a high throughput. Whereas in the case of a large array of data, we'll have a one instructions to process more and large data arrays. Whereas in the case of an algorithm intensive, so it will have a fast mathematical computation, single cycle DSP operations. Whereas in the case of an, so it is to system flexibility, whereas general purpose programmability, EEPROM, MCR, MP mode will have over on it. So, what are all the different approaches in order to have offline hardware implementations? High-speed general-purpose computers, so which is to be a programmable, whereas in the case of an expensive, it can be configured for different applications. So, we'll have a complex control, we'll have input-output overheads. Whereas in the case of an custom design realistic components, so it still have a fun efficient design, application specific, large throughputs, and will have a fun high development cost. Whereas in the case of a general purpose DSP process, so it combined the programmability and control features of general purpose computers and the architectural innovations of a special purpose chips. So we'll have often a high speed, low power, at the same time we'll have often low cost. So while we are saying about a general purpose computers, so it can be a flexible one. It is suitable for internet and multimedia applications. It will have a software intensive, so it is slow for high speed applications. It is too bulky and it will be the power will be very hungry over on it. Why are conventional processes are not suitable for DSP? So we'll have a caches or a very structured area. So we'll have a small register files, force, lots of memory access. These are different from cache since these are program managed. Whereas in the case of and complex instructions, issue logic, branch predictions, speculations, etc., which they are not needed for DSP. And we don't know how enough arithmetic logic unit functions. And it does not have adequate dynamic range and will have a patient range. So the next thing we have to see about an data processing versus signal processing. So what are you using on it? So usually general purpose microprocessors are designed primarily for data processing. Whereas the primary burden is to be that we have data read or write. Whereas in the case of a digital signal processor, microprocessor is specifically designed for signal processing. The primary burden is about mathematical operations. DSP architecture therefore incorporates certain features that found in general purpose microprocessors. Whereas in the case of an DSP requirements, so what we'll be having over on it, Abdina, emphasis is on mathematical operations rather than data manipulations, operations like word processing, database management, etc. Whereas design is optimized for DSP algorithms, which implement a fair filter, FFT generator, etc. Whereas the processing is also real time. There is the input signal comes continuously and output signal is also produced continuously as the input is acquired. But the case of a dominant mathematical operations is multiply and accumulate on separate inputs is parallel. What are all the features of digital signal process? So we'll have a fun caters to high arithmetic demands, real-time operations, analog input or output, where it has a large number of functional units for a given size, and we'll have a small control logic. So these are all the informations which is also helpful for in a unit 5 also. The thing is to be that because the unit 5 says that about what about the digital signal processes, what about the DSP architectures, and what about the DSP applications, and what are all the DSP addressing modes which are all behind over on it. So that will be carried out over on it. So far we have seen about that how the DAZ and ADZ which is performed, what are all the features, what are all the characteristics which is behind in the case of an DSP processes. Okay, next we can see in the next class. Thank you all.